Good afternoon, folks. The session we're going to be talking about this afternoon is an MPI-IO Cloud Cluster Bioinformatics Summer Project. My name is Dougal Ballantyne. I'm a solutions architect with Amazon Web Services. I'm based in Seattle. I work a lot on our HPC offerings and capabilities. And I'm going to talk a little bit, if my clicker goes forward, about file systems on AWS. What I'm going to talk about is some of the building blocks that the AWS platform offers, some of the components you can use, some of the things you need to think about when you're building a file system on AWS. And then I'm going to hand over to Boyd and Brandon, and they're going to talk about actually deploying the OrangeFS file system on AWS as part of a larger project. So a little question, what file system must you use on AWS? I get this question a lot. And to be honest, the answer is the one that meets your needs. There is no file system on AWS you must use. There's no file system on AWS that you have to use. You use the file system that makes the most sense for your environment. And I cover here sort of a set of questions I expect people to ask themselves as they're looking at file systems. And these questions are relevant if you are doing like instance-based file systems, so ext3, ext4, NTFS, or moving up into distributed and replicated file systems as well. So you need to really get an understanding of what are you going to do with the file system and how are you going to use the file system. One of the nice things about AWS is we offer a whole pile of building blocks. So there's lots of different components on AWS, from EC2 and then the EBS volumes. S3 is also a solution for storing data. And all of these building blocks together help you form a file system. And so it's about understanding those building blocks, what they deliver, how they perform, so you can build the file system that you want. I'm going to talk a little bit about the building blocks we offer today. So we have the Amazon Elastic Compute Cloud, EC2. They range from very small instances all the way up to very large instances. Our largest storage instance today comes with 48 terabytes of storage, 24 2-terabyte drives. They come with lots of RAM, so you can do like RAM-based file systems or have lots of RAM in the cache servers. Different networking capabilities, so a shared network where you're basically sharing the network with other traffic on your instance. So if you're serving a lot of content out to clients, then you're going to be sharing that with the traffic to EBS. EBS optimized, so you can have a dedicated path to the EBS infrastructure. And then we have 10 gigabit networking on our larger instances to enable you to have 10 gigabit to EBS and 10 gigabit node to node. We have Amazon Simple Storage Service, or Amazon S3. Unlimited capacity, you pay for what you use, not what you provision, so you can just keep putting objects in and only pay for what's there. Web scale, when I say web scale, I mean it scales horizontally. So the more clients, the more connections you point to S3, the more throughput, more capacity you're going to get out of it. Supports some features like lifecycle management, the ability to cycle content out of S3 into Glacier or delete content after a predetermined amount of time. Some of the more low-level building blocks in there is the local storage on the instances. So I mentioned that a little bit in the large instance, the 48 terabyte, but almost all of our instances have different ephemeral storage available. Some of them have SSD-backed storage, some of them have hard drives attached to them, and each one you can choose will deliver a different amount of storage and also performance. It takes too long here in the talk to go through each individual one, but we cover them on our website, and also it's worth benchmarking each instance to work out the right one for your application. They are free in the sort of sense of the term. It's included in the instance cost, so when you provision the instance, the storage is going to be there. Amazon Elastic Block Store, 1 gigabyte to 1,000 gigabytes of storage, standard and provisioned IOPS. Standard volumes deliver about 100 IOPS per second. Provisioned IOPS up to 4,000 IOPS on a volume now, and you can choose how many IOPS each volume needs and configure them appropriately. To build out larger environments, you can have multiple volumes on an instance, and you can snapshot these volumes into S3. And when you snapshot a volume into S3, you can recreate that volume in any other availability zone within the region, and even copy those snapshots to other regions to recreate storage solutions in another part. We have a dedicated set of storage-optimized instances. Today, these are the HI1 and HS1 instances. HI1s are SSD-based, so we have 2 terabytes of SSD, and the HS1s are direct-attached hard drive instances, so 48 terabytes of storage. We have EBS-optimized instances. I touched upon those earlier. These are critical when you're building an environment where you don't want to have any contention on the storage network for the volumes you've provisioned. So the 4 questions I like to ask when I'm trying to put these building blocks together is temporary or long-term storage. Am I going to store it, just for the duration of the simulation or the cluster run, or is this something I need to keep for a very long time? Maybe I need to keep it for regulatory reasons. Is it going to be shared storage that everyone's going to be using, or is it just the instances or the servers who need to have storage for them to be able to compute? How much storage do I need, and how fast? So long-term storage. Typically, long-term storage we address with Amazon S3. You can pull the data sets from S3 whenever you need them. So this enables you to build on-demand clusters, on-demand file systems, pulling the data sets down from S3, where you've got long-term storage at low cost, and onto a file system that you've deployed, like OrangeFS. You can easily do it with AWS CLI. This is a new CLI we launched about 2 months ago. And now enables you to do simple bash scripts or incorporate them into your workflows to do AWS CLI, S3, CP, and then point at a bucket or a file system, and it will copy the data backwards and forwards using multiple threads and multiple streams so you get the most utilization of your bandwidth. And we touched upon it earlier, life-cycling to Glacier. Temporary storage. If you need temporary storage for your simulation, the first place to look always is the ephemeral storage on the instances. The storage is going to go away if the instance goes away, so it, by definition, is temporary. Building out a distributed file system on top of ephemeral storage enables you to have a shared Scratch file system. And a couple of products we list here, OrangeFS we're talking about today, Lustre, Ceph, and there's lots of other file systems you can deploy on top of those that give you the ability to take that ephemeral storage and scale it up so there's more. And when working with this, you can pull the data down again from AWS, Amazon's storage service, and when you pull that data down, you can then use it for the cluster. How much? These are just some pointers when thinking about how much. With S3, you're only paying for what you use, so you don't really need to think about how much. It's going to be, when will I access it? How long do I keep it? With EBS, you want to make sure you're only provisioning the volumes you need. So you're going to pay for the storage you provision, so you should only provision 10 terabytes if you need 10 terabytes of data. The how fast question. So ephemeral storage is always going to deliver more throughput than the EBS storage or the other storage solutions put together because it's directly attached to the instances. On our high storage instances, you can deliver up to 2.2 gigabytes of storage throughput sequential I/O. On EBS, you can deliver a lot more IOPS. And so there's times where you want to use EBS over the ephemeral storage because it's going to deliver more IOPS. And with Amazon S3, it scales horizontally. So if you have hundreds or thousands of clients needing to access data, S3 is going to be able to scale to that without you having to adjust anything in the back end. Making those file systems persistent. So if you are using some of those file systems which are Scratch-based or you want to have some data persistence over failure, look to using EBS block storage or EBS snapshots or the replication in some of the file systems like LusterFS. And we're going to talk a little bit about automating deployments. So we're going to talk about it in the talk afterwards, but CloudFormations is a templating language from AWS that enables you to define what a file system or an architecture you want to deploy looks like. So utilizing CloudFormations, you can make up a file system architecture which is parameterized, so number of storage servers, number of volumes, and then only adjust the parameters to still deploy the same file system. Makes it easy to set them up and tear them down, introducing the concept of on-demand file systems. And you can also track any changes to your templates in a source code management system like Git or SVN, so you know what version of the template is being used by what team or what person. So to wrap up a little bit in my introduction here, some of the solutions I talked about are available on AWS today. So we have OrangeFS from Omnibod, who's going to come up and talk next. We have Red Hat Storage, which is GlusterFS. And we have Intel Cloud Edition Lustre, which is also available in the marketplace today. And with that, I'd like to bring up Boyd and Brandon to talk about OrangeFS on AWS. Thank you. Thanks, Boyd.
Well, great. Thank you for coming out. We're looking forward to the opportunity of speaking with you. We had this idea, so we're trying to look at having a real use case. And so we were working with some professors and some researchers at Clemson University. And they essentially had the idea of taking this RNA sequence differential gene expression workflow, the whole mouthful there. So there's a couple professors there. You can see Dr. Alex Feltus and Duffy and Dr. Von Olsen. And they were looking at this workflow, and they're trying to figure out how to optimize it. And they said, well, hey, if we take parts of this, let's figure out how we can optimize it, and let's try to run it in the cloud. So they said, well, hey, we need someone to work on this. So they said, hey, we have a summer intern here this summer, and Brandon got elected to do that. So we worked with Brandon and the researchers to go through this. So what this is a real use case of using a scale-out file system in the cloud, as Dougal kind of highlighted and went around. So let's go through this. So a little background. OrangeFS, as Dougal kind of highlighted, is one of the parallel scale-out file systems that you can run in Amazon. And this kind of diagram, as you can see you have an OrangeFS instance, and we chose to deploy this scale-out file system on top of EBS volumes. So we had 8 EBS volumes underneath each of the OrangeFS instances. And then as you can see on the right of the diagram, we scaled OrangeFS over 4, 8, or 16, depending on the tests we were doing, to get a shared scale-out file system so we could do this genomics workflow. And the clients we actually configured and set up to do MPI-IO and some of the custom code, MPI code, to really provide this performance enhancements to this workflow. So as you can see, to kind of make this go beyond what's available in the marketplace, as the previous slide, where you just kind of have OrangeFS and some things you put in, we also added the concept of a scheduler. We used Torque and Maui for these experiments, so you could submit the workflows. And we also used WebDAV to get the information, get the big data sets up into OrangeFS, the file system, so you could do the work. And we could have easily stored those for long-term persistence in S3 and then translated those to S3, just as Dougal highlighted earlier. So as you spin up, and kind of what we're going through in this presentation is you'll see that, well, a CloudFormation template, and as we go through that CloudFormation template, all of these various things will be set up. So you'll see the VPC get set up, so it sets up a virtual private cloud. We spin up an Amazon DynamoDB, and that's essentially so each node can go up and register and wait for all the other nodes to come up that are going to be in the file system or as part of the clients. And then, once they're all up, then the rest of the configuration can happen. And we'll kind of walk through that. And then the Torque and the Maui are also spun up, and OrangeFS WebDAV. So essentially, with the AMIs that are sitting out there and this CloudFormation template, you can essentially build a whole on-demand cluster that you can do your workflows with. So I wanted to highlight kind of some of the prompts as you would see them in a CloudFormation template and some of the other key aspects. And then as you kind of look through this isn't the full template. It kind of would be hard to see on the screen. I didn't want to go through it very much. But I wanted to highlight these key aspects as we go through this. And then Brandon's going to come up and do a demo. And because we were scared of Wi-Fi, we actually did a screen cam of a demo. But you'll be able to see that. So there's various things in a CloudFormation template that you can set up that you can prompt the user for. And you can prompt them for lots of things or very few things. And as we were setting up OrangeFS to be as part of the AWS Marketplace, we determined that, and we're educated, that fewer is better. So here's, as you can see, here's the key name, the VPC ID. The reason we reference the VPC ID is you might already have a virtual private cloud set up that you want to leverage, or you may want to spin up a new one. There's the public subnet, so you can have your NAT instances talking out there. You also have a private subnet. And then there's restrictions, so if you want to restrict access to your public-facing things, you can do the access from. And then part of what I mentioned before was the DynamoDB. So we actually use DynamoDB for the FS config and also the worker config. So they all line up, register, wait till they're all ready, then they finish their config using Cloud Init. So you run through and you have Cloud Init going through and finishing it, setting them up after they're all up and running. And here's the things you need to do to kind of finish setting up the IAM and the network pieces. So you pull all the pieces together, the root profile, host keys. There's the private subnet that you put in the input parameters before. There's your route table that links pieces together. Then the association. And then there's your ACL. And then finally, there's the EIP, which is the elastic IP address, and there's actually 3 of those in here. I just highlighted it with 1. So you have those public addresses for your NAT, your WebDAV server, as well as your scheduler. And as you can see, here's the kind of devices that we used. And you see it's pretty straightforward as you go through this. And there's some other things in the JSON you need to edit and go through, but it's a really straightforward process of building these CloudFormation templates. So there's a NAT device. The master coordinator is what we call the scheduler. There's the OrangeFS fleet. And if you notice, it's a little different. It's an auto-scaling group. So it auto-scales to the number of nodes you need, and that's configured within the template. The worker fleet, same thing, auto-scaling group. And then also the WebDAV is just an instance sitting out there. And if you notice, the NAT, the master, and the WebDAV will have the EIP that I mentioned earlier. So it's accessible from the internet, or however you want to set up your network. So here's kind of the magic behind it. So after you're going through all this stuff, then there's a Python script that runs. So each instance comes up, and it executes what's called cloud-init, and then cloud-init says, hey, run this. And in this case, this is a Torque master config. There's also an OrangeFS config for those types of nodes. And you pass all these parameters in so you know, hey, this is the number of workers I'm waiting for. Here's the fleet size. Here's the ports I want to configure. You know, here's the FSID so I can contact the file system that's in there. So you just pass all these things in from the CloudFormation template. So each node knows about these. And part of this Python script actually sits and polls and waits the DynamoDB, polling it each time, and waits for all of the other instances to come up. And it says, hey, they're all up and registered. Finish configuring. You know, do all the stuff that you need to do. You might need to know the IP addresses of the other machines so they can communicate, or various other things. Dougal helped me work through all that. He's a great help, so rely on him. And so we're actually postponed the demo to the end, but the one interesting thing through all of this is a lot of this work that was done with the worker configs and all those things was actually done by Brandon. We actually kind of figured it out when we were doing the file system, that Brandon came along and added all those other pieces in. So here's kind of the expression workflow. So there's kind of 2 main parts. You can see over to the right, there's this big, long workflow, and you can go through to kind of do all the various different aspects you need. But there were 2 processes that took a really long time. And we really wanted to focus on, hey, how can we make those faster? That's where we were working with the research scientists, and they came in and said, hey, if we turn these into MPI-IO jobs, they'll get a lot faster. So the first one that they did was the fast queue splitter, and then also the merge. So you have the splitter and the merge. So the splitter is the first process where you're saying, here's my sequence, and then you start breaking it up into lots of little places so you can actually do the work on it. And you'll see some numbers. I'll let you wait and see what the numbers, the performance numbers we got after we did it. Then also the same thing was the merge, kind of the back, I've done the work, and then a merge back. So there's kind of a very small snapshot of the 12 gig file that we were working on. And this is a sample Torque Maui job. So this is kind of all the different pieces you need to put in place. If you notice, there's an MPI run, and then this is actually the fast queue. So, and then the results kind of go out. And then the wall time kind of lets you know how long it runs. So for the fast queue splitter, the original work that was done was essentially kind of the old method. If you looked like it took over an hour to run. And this was on native hardware running. And it's like, okay, it takes a long time. You start doing many of these, the time adds up. And so Brandon actually went through and ran a series of tests and took the average numbers. And with CC2 8x large, you can see that it's well under 20 seconds. It's a little over 10 seconds to run, which used to take an hour. So it's pretty impressive the performance gain you can get at the same time moving something into the cloud or in AWS. And then there kind of gives you a difference between the M3 extra large as well as the M1 extra large, so you can kind of see the differences. And to keep things simple for the tests, Brandon actually just used the same instance type for the file system as well as the compute node. So you could probably mix some of that and get some tuning, but just for simplicity's sake. And then for the merge time, that was over 2,000 seconds. Same type, same type of drop down to a little over 10 seconds, 10, 15 seconds for the 8 extra large. And then the M3 and the M1, you could see kind of grew from that a little bit. But the M3 extra large actually performed it's a little closer on this one relative to the other one. So workloads always vary, so you need to go out and do some tests and try some things, try some different instances, and determine what's the best thing and the best type for your workload. And obviously, when you're all done with doing these tests, you get to turn it all off and you don't have to pay anymore. That's one of the big advantages. So turn it over to Brandon, who will get to come up.
Okay. All right, so as Boyd said, I was the one that got the task assigned to work on this project, and I'm basically just going to take you through a brief demo of starting the job, running the job, show you how it's done, how easy it is to do once everything is actually up and running. So this is where you go to create the stack, which is from what the CloudFormation template's used for. It creates a stack of the instances and everything that you need to run. So this is the starting screen, and let's start the. All right, so basically, obviously, you're going to click the new stack button. Then you come up with the prompts that say, name your stack. So name this AWS cluster demo. And then you get the chance to either use a sample template that's provided, or you can upload a template file. And in this case, we're going to end up uploading a template file, which is the CloudFormation template that Boyd referenced, that has all the information needed to spin up all the nodes. And so after that, you'll click your continue. And these are all the areas that Boyd talked about filling in, like the VPC ID, the key name, and all the stuff that's necessary to access your data and secure it. And you have to click this little checkbox about the IAM resources, because it also needs to be able to access the DynamoDB and create calls. So this is, you tag your instances, and basically you just give it a name, so you can say, okay, if you have a bunch of instances running, you know which instances belong to this stack, which is what that is going to do. And then it gives you a brief summary sheet of, okay, this is what you want to do. It tells you all the stuff that you entered, all your parameters. You can double check before you start creating your stack. So then after you create the stack, it comes up, and this is the window that will show you what's being created and when it is being created and how everything is complete. And we're going to jump ahead here a little bit to where it creates, because we're not going to sit and wait for everything. So as you can see, it's creating the master coordinator, the WebDAV device, and the, what's the other one? The WebDAV. And also you can see it's creating the OrangeFS configurations and the worker fleet configurations as well. And the EIP, the elastic IP address, as Boyd talked about, that'll make it accessible from the public internet. So right now, the WebDAV server and the NAT actually are the only two that have the EIP address, because you don't want people to be able to get inside. You don't want people from the outside world to be able to get into your data. So, and then when it's all done, it'll pop up and say, okay, your stack creation is complete. And so now I'm going to SSH into the WebDAV device, the WebDAV node, by using the EIP. So I get to the WebDAV node, because in order to access the internals, the WebDAV and the NAT are the two instances that can access the internal network. So in order to get to the internal cluster, you have to go through and have the right credentials. And now I'm going to jump over to the Amazon database, the DynamoDB, and you can see it has a table for the workers as well as the OrangeFS configuration. And like Boyd said, this is basically so that the nodes know when all the instances are up, because you don't want to spin up your file system if all the nodes haven't been created yet. This is the workers. There's 8 workers and 1 master, but since that combines them all into one list, so there's 9. And then this is our OrangeFS fleet, and there's only 7. There actually should be 8. That'll be fixed here momentarily. And so now we're going to go back and actually SSH into the actual cluster, the master node that's running the Torque and Maui scheduler, where you can submit your jobs with whatever work that you have, the scripts. And so we're going to let it do that. And basically, the whole point was to make it take all the guesswork out of actually having to learn how to use all the underlying technology. So that way we can take people who are a little less code efficient with like MPI-IO and everything can do this. And so now it's running the cloud init script that he was talking about. And that highlighted right there. But this is running the master, since I'm on the master node that does the torque and MAUI, it's running the master scheduler. There's different configurations for just the workers, the scheduler, and the web dev device. And so it's gonna run all that. And now I went ahead and skipped through the loading and running all the scripts. And now you can see all the daemons for everything are running. Torque is running. We even have Condor. Condor is an option too as a scheduler if you want to use that. And OrangeFS has been set up and mounted. And I actually went in and I uploaded the data set using the 12 gigabyte. We used a 12 gigabyte file because a lot of the latency between transferring the files. In fact, we wanted to scale larger scale, but that was the biggest data we had at the time. And I've already uploaded that because it takes longer depending on your network configuration, so there's no reason to sit through all that. So I changed into the OrangeFS directory, which is just like a normal Linux directory. It's mounted, but all the nodes know that this exists. So all the nodes in the cluster can access this file system. And so as you can see, there's our 12 gigabyte sample file over there. And now I'm showing, this is the script that he referred to earlier. There's a couple extra things in there for debugging purposes and all that. I'm actually going to go in and comment that out because I didn't realize when I was running the demo that I don't want it to delete the file so you all can actually see what's going on. So let it do that. But this is for the benchmarking that we did with those numbers that you saw. This is the scripts that we actually ran. And I'm going to also take it so that it doesn't pipe out the text. But we did, when this actually runs, the time difference is actually quite nice compared to sitting for 3 hours and waiting for your data set to run. And so now I'll show you that the torque is actually running. There's 8 different nodes. These are CC2 8x large nodes that are running right now. And they're all free right now. We set up the MAUI configuration too to where each one of our, each job will split up across all the 8 clusters. It won't try and dump them all onto one node so that one node's hammered with all the I/O and all the processes and stuff like that. So now I'm going to submit the simple script that I showed you earlier, the one-line script. And I should do that. All right. And so there's job 0, it's the first one. So now I'll show you simply that as you see the job, under the jobs it is listed as it's all the job 1. 042 is split up across all 8 nodes with the one node free at the top. And actually, in the time it took me to show this on the screen, the job has actually already completed. It has split the 12 gigabyte file into 8 different pieces, about 1 gigabyte and 1.5 gigabytes each. As you can see on the screen, it's split it up, and the time it took me to just scroll up through the list of nodes that was there, it's already done as compared to the 20, 30 minutes before. And so now, I'm going to fast forward a little bit here, and I'm going to show you also we did the merge. Well, no, this is showing the results. See, it took it 4 seconds to read, 7 seconds to write versus 20 minutes to read, 30 minutes to write. And a lot of that has to do with using the MPI-IO and the file system itself, because it can multiple processes, which with using MPI, it's split up across the nodes. Multiple processes can write to the same file at the same time and simultaneously, so that way it speeds up writing a little bit more. And so now we're going to do the concatenation, which is the reverse of what we just did. It's going to take all the 8 files that we just generated, and it's going to merge them all back into a 12.5 gigabyte file. And it's going to run at about the same time as the original read. And I think it's going to skip a little bit here. Maybe. Yeah, okay, skip ahead to, this is basically me just showing, this is the same script. I changed one line. I changed the concat to the divide to concatenation. And so I'm going to do the same thing here. We're going to just submit this script, and it'll go through. And then I'm going to show, again, it's going to show that the the nodes are all assigned to one job, and everything is running as it should be, just to show that we're not just putting 12 files out there and saying this is what is actually, just to make sure that it's actually being done. There's the proof. It is assigned to the 8 different nodes. And in the same time that, yet again, the same time that it took me to do that, this check the job status, it's already done. And so now you'll be able to see there'll be a combined FASTQ file up there at the top that is the same size as the original FASTQ file. It took the 8 pieces and combined them into the single file in, I think it took it about 12 seconds. I'll show the time command here in a minute. I think it's going to do a, yeah. It's going to cat out, the jobs came back, there's no errors. And this is showing where each process writes to a different offset in the file. So this is for the file system. And then we're going to do the time to prove. Took it 12 point some seconds, which compared to, yet again, your 30, 45 minutes is a big speed increase. And so that's how simple it is once you went with what we're trying to do with deploying the file system, the scheduler, and everything. All you have to do, it's as simple as uploading your data, having your script ready, submitting it, and hopefully if it gets better, and then it gets better times. So I guess now we're going to do questions.
Yeah, we'll go ahead and I wanted to kind of to follow back and kind of review a couple of the points. And just to kind of highlight, it's pretty impressive. I mean, Brandon did a great job. This is a summer project, kind of taking this from here's just a file system, and then here's all this extra work to get all these other pieces working, the jobs to submit, getting MPI clients all out there, getting the Torque and Maui to work. We actually had them do Condor first, and then said, oh, here, let's, because the MPI jobs, let's go and switch it to Torque and Maui. So he did a great job. Kudos to him, just keeping striving and plugging through. But kind of here's a review of what it was. So you have your Torque, your Maui. The CloudFormation template essentially was broken into 2 parts. So you have your MPI-IO clients. Those are the workers. You have your OrangeFS servers. They kind of went out and provided the data. And Amazon, the DynamoDB, was basically there as a placeholder so you could register all the devices, wait for them to all come, and then go. It kind of prevented the need of having a monitor node kind of keeping an eye on things, because what happens if it goes down? These are essentially all there, and they can be up and available. You submit your jobs to Torque and Maui. Through the job, you upload the data, again, OrangeFS and WebDAV, and it was pretty impressive. And the researchers were really floored, because one of the research developers, did the work to kind of for the MPI-IO job, but the fact that you could take this, deploy it, run both sets of jobs, shut down the cluster, and have that all done in minutes, much less time than any one of these single steps. So it's actually a pretty impressive workflow and was very nice. So yeah, so go ahead and we'll have Q&A now.
Yeah, so thank you very much, Boyd and Brandon. It's a really great example of putting a lot of the AWS services together into a whole solution and helping the researchers. So we have plenty of time for questions, and obviously if you guys can stay up and help with the questions. So if you could use the mic just because we're doing the recording, that would be easy, or I can repeat the questions for you as well. But
have you guys measured the interconnect on how does the interconnect on the AWS affect your performance?
So for this job, and that's why you saw the CC2 performance versus the others, was because it had the 10 gig interconnect. So you could see this is an IO intensive, so that network interconnect, depending on your workload, will be something that you want to choose those instances that have that higher bandwidth.
First of all, it's extremely impressive. I was doing something like that, and the thing that you showed is just wow. I have a question. What advantages does having OrangeFS give you versus just having EBS mounted and kind of mounted from all the clients? What did you achieve by having OrangeFS?
Right, so if you noticed, each of those nodes were made, you know, basically there's a local file system as part of the process. So there's XFS on each one of those nodes spread across all the EBS volumes. And then layered across all of those as a unified shared file system, that's what OrangeFS does. So it takes your I/O and your network pipe essentially over those and adds them across all those. So you get the aggregate bandwidth of all the nodes available to the clients. So when they're doing their work and the files are striped across various portions, various of those nodes, you get the higher throughput and the higher performance.
Did you have a chance to compare the performance with or without OrangeFS? The throughput, I mean, how much advantage would OrangeFS give you?
Yeah.
I can take that to a certain extent. So an EBS volume is attached to an instance and can only be attached to one instance. You can make snapshots of EBS volumes and create more of those volumes to attach to more instances. But the workload that they were tackling required multiple instances, all of the workers being able to access all of the data at the same time, and that necessitates a shared file system. So they're taking the EBS block storage and then layering on top of that OrangeFS. So you can't really repeat the experiment unless you ran a single node only with EBS only. Does that make more sense?
It also helps that instead of, because where it runs MPI, each process needs to have access to that specific file. Like you're running the same file, the FASTQ file, you're splitting it up into 8 parts. Each process is accessing that file at the same time, trying to get that data. So instead of having to copy that data to each node, it's in one shared place where each process can access it.
Yeah, I'll just repeat the question. So the question was, would it be possible to split the files and distribute them to the nodes? I personally can't comment on that. It is a different approach that they could have taken, but I believe the approach was to use MPI-IO and split them in the MPI model rather than the file itself.
Right, and as part of that is, you know, you split it, you do some work. There's a few steps in that workflow where other things and other analysis had to happen, and a lot of those are CPU intensive. So actually doing this in that distributed fashion allows them to have access, and then merging back allows it. So it's really that shared nature, and some of those can actually, depending on the type of workflow, can actually need to access other parts of the files that would then be on different systems. So it really kind of needs shared access.
So the CC2X large instances have a fair bit of ephemeral storage. Have you thought about tying together the ephemeral storage with layering OrangeFS on top of that, or have you only played with EBS?
Yeah, we actually, when we first kind of started playing with it, we set that up. And so, yeah, it works the same way. You just kind of say, okay, put XFS here versus XFS there, and then layer OrangeFS over the top, so it works just fine.
The MPI versions, MPI-IO versions, splitter merge, is that available publicly?
Yeah, if you send me an email, it's actually out on GitHub, so we can actually give you access to that.
Parts. Did you look at using Gluster and compare Gluster to OrangeFS? And I'm actually kind of curious if you pushed how many alignments you were able to push on the file system, if you tried to see how many you could run simultaneously.
Yeah, so, and that's kind of the next steps. We're actually completing that whole workflow. So that's kind of the next steps behind this. So again, if you shoot us an email, when we get through those different steps, we can let you know, because that's kind of the next things that we're going into, is going through that whole workflow.
Okay, well, thank you very much, Boyd, Brandon. I appreciate you coming in today and talking, and thank you very much for your time, folks.